Welcome to the next video, everybody. Today we're going to finally finish the proof of Theorem 14.3.1. Let's get into it. Here was the theorem. So this is one of the earlier videos in this chapter. It says let E over QP be a semi-stable elliptic curve. If E has either ordinary or multiplicative reduction, then rho EP, so that's the p-adic representation attached to E, is isomorphic to epsilon chi star 0 chi inverse, where epsilon is the p-adic cyclotomic character, and chi from GP to ZP cross is a continuous unramified character. In particular, rho bar EP is omega chi bar star 0 chi bar inverse, where omega is the mod P cyclotomic character, and chi bar from GP to FP cross is a continuous unramified character. So we proved all this already. What we didn't prove is the next part. If instead E has good supersingular reduction, then the two-dimensional FP representation rho bar EP, when restricted to inertia at P, is isomorphic to the fundamental character of level 2. Moreover, rho bar EP is absolutely irreducible, and when you tensor it up to QP, it's irreducible. Okay? So by what we have already shown in the discussion prior to Theorem 14.3.4, so that's our most recent theorem, it suffices to prove that in the supersingular case, we have irreducibility. Okay? This will follow immediately. Okay? And then what will allow us to conclude this part? Well, if we can prove that this representation is irreducible, this will allow us to apply Theorem 14.3.4 with k equals fp squared to conclude immediately, thanks to Theorem 14.3.2. So Theorem 14.3.2 gives you the flatness of the torsion subgroups of E, which allows you to apply Theorem 14.3.4 to conclude that by irreducibility, your representation is isomorphic to the fundamental character of level 2. That's this 2 here, essentially. Okay, so, go back and review those theorems. So we're using Raynaud's theorems there. Okay, so we're just going to prove that in the supersingular case, this representation is irreducible. Okay, if it were reducible, then by Theorem 14.3.3, so that's Raynaud's equivalence of categories, its diagonal characters are ZP unflat. Since det rho bar EP is omega, so we've known this guy has cyclotomic determinant for a while, Theorem 14.3.4 and the fact that the level 1 fundamental character is nothing but omega restricted to I sub p show us that there's a short exact sequence of the form 0 to psi 1, which is the first fundamental character, which is omega restricted to IP, to chi 2 to 0, where what are these characters here? They're chi 1 and chi 2, and they are just omega restricted to IP and the trivial character in some order, okay? So this is a little exercise that you should go back and do to make sure you have a good grasp of the theorems that have been used so far. It's a very easy exercise. Okay, so we have the short exact sequence here. Okay, now by Theorem 14.3.3, there's from that exact sequence, you can make another short exact sequence of finite flat ZPN group schemes, 0 to G1 to cal E un bracket P to G2 to 0. Which on QP bar points realizes the given decomposition of rho bar EP restricted to I sub p. Where what is this cal E un here? It's the neuron model of E over QP un, which is a curve of good reduction. Okay, so this is the maximal unramified extension of QP. We will need the fact that this model has supersingular closed fiber. How do you prove that? It's easy. So the J invariant of E over QP un is just the J invariant of E over QP, and that's integral because E has good reduction. Okay, and the image in FP bar of this J invariant is just the J invariant of the closed fiber, but the J invariant determines reduction type. Okay, and so the claim follows. Okay, great. So let's assume that P isn't 2, which is the only case that we're going to need. Okay, when you do that, you get that omega restricted to IP is non-trivial. Let G denote whichever of G1 or G2 from that exact sequence above has trivial generic fiber representation. Like one of these has to have trivial generic fiber representation because one of these characters is trivial, right? Okay, we claim that G is étal. Okay, let's. How are you done if you can prove that? If we assume this, then when you pass to the closed fiber, this would prove that the étal factor of the finite flat group scheme cal E un bracket P tensored up to FP bar is non-trivial, so that there exists a non-trivial P torsion geometric point on the closed fiber. Okay, but that contradicts supersingularity. You can't have non-trivial P torsion when you're supersingular. Okay. And remember, the closed fiber is supersingular. So We have supersingularity to contradict in the first place. Okay, so it's enough to prove that G is a tall. So how do we do that? Well, you're sort of now reduced to proving something more abstract, but sort of a lot more limited in scope, which is the following. When P isn't 2, we're now reduced to proving the claim that if H over ZPN is a finite flat group scheme with P power order, and the QP bar points of H have trivial inertial action, then H viewed as a ZP unscheme is a tall. Okay. So how do you prove this? The generic fiber representation of GQP un, which is just inertia at P, is trivial, right? So that's given. So the full faithfulness part of Raynaud's equivalence of categories tells us that H over ZPN is a constant group scheme. Okay, so that's by this triviality. Well, if it's a constant group scheme, then it's a tall over ZPN. Great. This you're just done, right? So this completes the proof of theorem 14.3.1 in the case P isn't 2, which is the only case we'll need. I will just tell you, though, that this theorem is true when P equals 2, and you can see CSS for a proof of that. It's quite a bit more difficult, as I recall, but we don't need it. So, we're just going to keep pressing forward, what we're doing here is we're slowly heading towards kind of Ramakrishna's results from his thesis on the flat deformation functor. So we're kind of building up some motivating results and some results we'll actually need also to attack that problem. So thank you for watching, and I'll see you in the next video.